Okay, we can start. So thank you so much for coming. Welcome. And we will start our night's webinar. So before diving into the subject, I just want to let you know that this webinar is part of a series. We are organizing webinar within the project EUPEX. EUPEX, which is European project, we started in 2022, and the goal of this project is to design and deploy a European pilot platform integrating hardware and software technology from Europe. Um, Within this project, we are also organizing webinar to showcase and um, share the result of the project and the lesson learned. And we have experts from the project showcasing their application and also the tools developed in the project. Um, we are mainly organizing monthly webinar. Um, but now our next future big event will be a workshop at High Peak. It's a conference that you may know, and this will be the 28th of January in Krakow. So if you are interested, the registration is not open yet, but you can still yeah, take a look. I will communicate on social media. You can also follow us on LinkedIn, and here you have some information. All our webinars are recorded and posted on our YouTube channel. You have the link here. I will send you the slide after the webinar. And yes, now that is said, let's move on to today's topic, our next webinar. It will be dedicated to BigDFT, a computational chemistry software package that uses wavelet-based density functional theory, DFT, to simulate electronic structures. Today, our speaker is Luigi Genovese from the CIA. Thank you so much, Luigi, for participating to this webinar and for sharing your research work. So just let me
A pleasure.
introduce you. Um, Luigi is a computational physicist with an education in theoretical high energy physics. His current research focuses on the conception, development, and implementation of new theoretical algorithms and methods that leverage advanced computing resources. These approaches enable large-scale quantum mechanical calculation across diverse fields, including solid-state physics, quantum chemistry, and electronic structured studies, with application in life science and biology. Now I will let Luigi present the hot
Thank you.
topic. And
Thank you for
yeah,
this opportunity, and I am happy to participate to this initiative. First of all, I would like to, of course, thank all the organizers for giving us this opportunity, and also you for your participation. I have to say that my headset may have some issues in hearing sound, so I can hear you now. But in case you have questions or comments, please feel free to put some message also in the chat. I will be very happy to interact with you also during the presentation of the material I would like to share. Um, Now I will try to introduce you with this, let's call it adventure of this big DFT code. I would call it like that because essentially this is an initiative that started nowadays. I think it's 20 years ago. We have been starting playing with wavelets for density functional theory. And I really think that this has become an adventure now because uh, uh, we started more by serendipity, essentially. We were mainly interested in seeing where we could go with this new formalism. And this was essentially very nice for us because we ended up by finding connections between different communities and different knowledges that are really challenging and stimulating. But let's first introduce what is the idea that lies below the BigDFT project. So it was a European project. In 2005, the CEA of Grenoble, where now I am, was the coordinator of a STREP project. This was a call based on exploratory initiatives. The coordination was among 4 different groups in Europe. The main idea of the BigDFT code was to develop a density functional theory code on a new formalism. I'm saying new for density functional theory community. It was not new at all at the time. The formalism is Dobeshi's wavelets, which is a set of functions, a framework, a basis set, more technically speaking, that was initially employed for signal processing. And the idea of using this basis was funded on the fact that when we want to express density functional theory calculation, we have signals that has to be brought to the computer, to the computational platforms. So especially when those signals are inhomogeneous in some sense, I would like to express that, a basis set like wavelets may reveal interesting features. So essentially, the main idea originally was to try to test the potential advantages of this formalism. We didn't have the specific goals or specific performance indicators at the time. We just wanted to see where we could get with this formalism. And actually, I think that it's interesting to manage the fact that indeed this formalism revealed to be very useful, and we could do many things that I will hope to illustrate today with you. Let's say the main points of them. Of course, there has been a new direction that has been opened. That has been opened thanks to that. So that's the main motivation. Try to see where a new formalism can really help in our community. Now, I will not have the time to discuss about wavelets today because this is a topic for applied mathematicians course, and of course it's not my field of expertise either. What is mainly important to somehow take into account is that wavelets is a basis set that has the property of being systematic. So the user can increase the precision of the calculation arbitrarily without any, let's say, difficulties, because it's like plane waves, where we have a indication of the completeness of the basis function that is easy to manage. In plane waves, you may know there are the cutoffs of the basis set. So the frequency of these basis functions is the main indicator to have a precise result. If you want a more precise results, you increase the maximum frequency of the basis set you are employing. In wavelet, if you want a precise results, you decrease what we call the grid spacing, which is the spatial separation between the position of those wavelets function, scaling function and wavelets are like plane waves, but they are localized, they are compact. So essentially it is as if we would have a plane waves approach, but conceived for inhomogeneous system, which means molecules, systems in a surface, system which have defects, because we can increase the resolution, the frequency in some sense of our description only where it is needed. So this saves computational power and produce at the same time precise results in the same spirit as we would use with plane waves code. I don't know if you are familiar with codes like Quantum Espresso, Abinit, BASP. All those codes employ plane waves for the basis description of the wave function in density functional theory. So eventually one end up with formalism that is naturally explicit. Essentially, you can simulate molecules on top of surface. You can simulate surface with electric fields. And you employ computational degrees of freedom mainly only where this is required for expressing the wave function, so what we call the Concham orbitals in the DFT community. Also, I have to say that I don't know how familiar you are with density functional theory, so I apologize in advance if I am using technical concepts that are difficult or somehow far from your community. So once again, feel free to put messages in the chat or to intervene if you want me to provide some clarification. In a density functional theory code, like in many other computational code, it's also interesting to mention that we need to solve differential equations, not only the Schrödinger equation that is solved iteratively in the density functional theory approximation, but also the Poisson equation. The Poisson equation is necessary to evaluate the electrostatic potential between the electrons that is felt by the electrons of the system. So we needed a efficient and precise accurate approach for solving this Poisson equation. And in this case, inside the BigDFT program suite, there is a specific library, which is the BigDFT Poisson solver, that is completely independent from the BigDFT code. It could be downloaded and installed separately. That solves the Poisson equation for real and homogeneous space grids for any kind of boundary condition. So this is another, let's say, outcome, another, let's say, sub-domain of DFT, which is the Poisson equation, where we also have been working in our last 20 years to exploit the benefit that wavelets provide for the community. And this is one of the library that is mainly used inside the EUPEX consortium to port the BigDFT formalism in the various modern high-performance computing architectures that we have access nowadays. So the main message here is that BigDFT is a large program suite which is made of different sub-libraries that all employ Dobeschi's wavelets to somehow express the computational framework. But there is also among this library the Poisson solver library that is also an objective of acceleration, because it's a general purpose library, because the Poisson equation is something that is necessary, is required in many fields of expertise. This Poisson's equation, Poisson solver is also capable to treat continuum media, so it's also able to treat what we call implicit solvents in computational chemistry. This is the main message that is main way in which this functionality is called. And in any case, the point is that it contributes to have a fully functional density functional theory code that is very precise, that is tailored for molecules or for systems that are inhomogeneous, and that can deal with different boundary conditions and external environments. So this was the initial, let's say, framework into which we have been using BigDFT. So we are more or less between 2010 and 2012, I would say. So we were starting using this code, and we started that we started to use that by taking profit its capabilities of very high precision. So where a high precision code is useful, but for instance, when we wanted to compare the energy of structures of different molecular systems that have somehow many different modifications between them. So this is an example of boron 80 structures. So at the time there was the study of boron fullerenes. That was a very interesting topic. So with the help of BigDFT formalism, we were able to demonstrate that such kind of molecules actually they have a energy landscape that is very close to glass like systems. So there are many different structures which lie in relatively compact energy range. So essentially having a code like BigDFT here is very valuable because you can increase the precision of your results, but at the same time you can treat systems that are isolated in a molecular sense in the same spirit of localized basis functions like Gaussian's based density functional theory codes that are mainly used in quantum chemistry or in computational chemistry. So this was a first direction of usage of this formalism. So the exploration of potential energy surfaces of different systems. This is an example with boron 80, but there has been many other calculations in the same range. So at some point, we wanted to increase our, let's say, domain where we could use this formalism. And as the name suggests, the BigDFT code had initially the idea of treating systems which were larger and larger because of the fact that wavelets enable you to save computational degrees of freedom. So we could go larger because essentially we have less memory requirements for performing a given calculation. And yet, there is the problem of the computational scaling. So the computational scaling of a density functional theory code within such kind of framework, the Consham DFT framework, is typically cubically scaling. So essentially, we have we reach a point where if we want to double the size of the number of atoms of your systems, you eventually need to use 8 times the computational resources that you needed to have before. So essentially, this eventually leads to a computational limit. So you can reach systems of few thousand atoms at most with this algorithm, but eventually you will be somehow limited by the scaling of the approach. Yet it's interesting, there is an interesting point because with the big DFT formalism, we have the possibility to design an algorithm for density functional theory that scales linearly with the number of atoms, so that we would only need, it would only require twice as much the computational power if we want to simulate twice as much the number of atoms. So 2012, as I said, 2014, we had the first motivation for a new approach based on Dobeshi's wavelets, which would enable the simulation of larger system. I would try to explain you in the following that this is just the first motivation. It's not the only one, and I think it's not the main one. We will see that having a linear scaling code, which scales linearly with the number of atoms, enables you to treat new science in a different way, thanks to the locality of the description. I already mentioned about the locality of the wavelets. So we know that the wavelets are basis sets that are compact. So they are somehow only living in a small region. Of course, they are defined on a grid. So essentially they can express delocalized quantities. For instance, in this cartoon, let's think about these molecule here where we express the wave functions, the Concham orbitals in a wavelet basis set, but they are delocalized on the entire molecule. An approach that enables linear scaling is instead of expressing these orbitals in wavelets, we can define an intermediate set of basis functions of degrees of freedom, which could resemble the molecular orbitals if we discuss in terms of quantum chemistry. And this intermediate set of basis functions will be then used to express the Concham operators and quantities. So essentially, we would have a two-level descriptions. Instead of using wavelets directly for the Concham orbitals, we would use localized molecular degrees of freedom for the Concham orbitals. And those localized molecular degrees of freedom are expressed in Dobeshi's wavelets. So if we would use a description or a terminology coming from computational quantum chemistry, it is as if we were using contracted wavelets in this basis, in this, let's say, algorithmic design. And then we can calculate the very same quantities as before, but by using this auxiliary intermediate basis set. What is the advantage? The advantage is that these molecular basis functions are naturally localized. So the corresponding Concham operators are provided by sparse matrices, and the manipulation of sparse matrices leads to linear scaling calculation, which are very suitable for very large supercomputers, but also for very large systems, because we save in this way degrees of freedom that would lead us otherwise to a cubic scaling behavior. So essentially, one can create those basis set and either fix them from the beginning or optimize them on top of the very chemical surrounding. So the advantage of this basis set is that they are very flexible in the sense that they can somehow be adjusted to the actual chemical property of your system. They can also be made quasi orthonormal. So we have a very, very small condition number. We have a very short spectral width of the operator. So essentially, this is a basis set that, thanks to wavelet properties, can be manipulated effectively, and one can even use this basis set in a fixed for a fixed set of fragments, and then replicate that in the various subdomains of the calculation. For this enable treatment of, again, inhomogeneous system, not only molecular system. Here we have a picture of defective surfaces. These are various defects on graphenes, where one can see where these chemical degrees of freedom are modified with respect to the non-defective description. So this is an example also that would enable us to perform different characterization of a system. Having such kind of algorithm that defines the degrees of freedom on the chemical properties of the system is something that provides new insights on the, for instance, what is the effective region surrounding a defect, how much a defect extends its influence to the neighboring regions, and so on. So those technical points are only based on the spectral width and the condition number of these basis functions. So essentially, the main point is that we have a second level of description on top of traditional Kohn-Sham cubic scaling DFT that is enabled by the locality of the Dobeshi's wavelet. So essentially, we have been able to solve the problem I have presented before about the scaling. So we have a linear scaling approach that is based on top of the cubic scaling approach, based on the localized molecular orbitals that are created on the fly thanks to the wavelet approach. Those localized can be created on the fly or fixed on some template calculations and then used once and for all, which essentially is something that would save computational time because you don't need to optimize anymore the basis set. So we have a kind of a hierarchy of treatments that could be linked with thanks to the fact that the underlying basis set is always the Dobeshi's wavelet. So we had a somehow computational framework, program suite, which would enable us to perform investigation of systems which are potentially very, very large with respect to what was traditionally calculated with density functional theory. We have to see, of course, it's important to say that the BigDFT is not the only DFT code which is capable to do so. There are other formalisms and other codes which try to solve the same kind of problems. Actually, we were at the time to ask ourselves what could be done with this kind of hierarchy of methods. So we have these molecular orbitals that we can call support functions. This is the name we use in our BigDFT consortium, that are localized and are built on top of the system. They are quasi-orthonormal, so the system somehow is telling you that those degrees of freedom are optimal for them. So we can use those degrees of freedom somehow to understand something more about the quantum system we are simulating. So it's kind of a mapping between quantum mechanical description coming from DFT, density functional theory, and localized information. So those objects can then be used in some way, for instance, to identify how a very large system is decomposed in terms of building blocks. If you have a molecule of 12 atoms, of course, this is not important. The entire molecule is your building block. But if you have a very large system of 12,000 atoms, for instance, if you have a protein, you may want to understand if the protein can really be seen as a composition of systems that are somehow can be treated as blocks of your system. If this is possible, we may want to understand how the interaction between those systems can be measured and how can be manipulated also. So somehow you see we are going into a framework where initially we just do simulation, computational description of the electronic structure, but then we can go towards the design of a system, or somehow from the understanding on how a system have different interactions that are playing together. So to make this discussion more explicit, I will try to provide a few examples on what we have been doing in the last 10 years, starting from linear scaling BigDFT calculations. First of all, there has been a series of reviews we have been writing in the past that illustrate that this is, once again, not only a BigDFT set of questions. There are a number of codes in the community that try to solve the very same, let's say, series of questions. In such kind of paper, you would find some considerations that could be helpful to orient yourself in this panorama of codes. The main message is to say that we need to change the way in which we use DFT calculation. Essentially, when you go to very large systems like the ones that are used in BigDFT, you cannot deal with the DFT calculation as if you were dealing with a single small molecule. For a molecule, you actually use the DFT in a very same way in which you would have used a force field, for instance. You measure the energy, you measure the forces, you move the atoms, you search for very precise optimized molecular structure, you search for synthesis pathways, transition states, and so on. So this is possible because the computational work for such kind of quantities is manageable, and also because the systems are unique blocks. There is no reason to split the system into various sub-blocks. At least there is little reason to do so. When you go to a system of 12,000 atoms, even if you're using a linear scaling code, it's linear scaling, but it's not faster than the small code. It's just linearly scaling, so you can simulate the systems. But it's out of question that you would do molecular dynamics or geometry optimization or synthesis pathways search with a pure DFT level of theory. The systems are too heavy, and it's also unnecessary to do so. The main point would be to use the locality of the DFT description that emerges from a linear scaling algorithm to understand more about this system. So this is another message that comes from the fact that we enable calculations that weren't possible 20 years ago, but we also have to change the research paradigm in this usage of codes. This is the object of another review paper we have been doing in the recent years that actually try to explain that. Computational complexity increases more and more as far as we go to larger system. And of course, this creates different the different research paradigms that we need to employ to somehow deal with such kind of computational complexity. So those are important points that I think it's meaningful to stress, because it's not just brute force. It's not just that you increase the size of your system and you could do the same with more atoms. It's not more of the same. It's opening new research avenues, of course, with the price of somehow changing the paradigms or creating new paradigms that are to be employed in this context. One of these new paradigm is this fragmentation of the system. So these are mathematical formula I won't discuss today, but the point is that within the DFT molecular orbitals of BigDFT, you can identify in these sparse matrices I have been mentioning before, recipes to decompose the density matrix of your system into subblocks within a given level of confidence. So somehow you fix an indicator that is something we have been calling the purity indicator. And this indicator is telling you under which extent it is legitimate for you to decompose the system into sub-fragments, into sub-portions of those systems. So essentially, I will skip the next mathematical slide, but essentially, you can decompose a very large system into small sub-fragments with a particular level of confidence given by this indicator. This indicator is totally agnostic of the property of the system. So once again, this is an approach which uses the Dobeshi's wavelets and the description of the electronic structure of the system without any prior knowledge. This is one of the main important advantages of using density functional theory, is that in principle it is an approach that doesn't require parametrization of your system. When it comes to systems that you do not know, it's an interesting property because you don't want it to. It's providing an unbiased description. And then once you have partitioned your system into sub-blocks, you can identify how strong is the chemical bond between these sub-blocks in the very same spirit of an approach of atoms in molecules, but here we have fragments in system of approach. So essentially we have this concept which we have been calling complexity reduction. So the idea is that this computational complexity can be reduced thanks to the advantage of localized degrees of freedom by dividing this system into meaningful fragment a posteriori without knowing anything before of this operation. So essentially, now let's move a little more, let's say, away from the original fields of DFT. We saw initially that we have been discussing about potential energy surface of boron cluster. Here we are discussing about inhibitor of a biological protein. So this is an example where we can see the atomic position of a small molecule. This is alpha ketamide inhibitor of the SARS-CoV-2 main protease, which is put into what we call an enzymatic pocket. So for those who are not familiar with such kind of figure, you should imagine that this surface here is just a contour surface which represents the vicinity of the protein position. So from the point of view of BigDFT, there are only atoms here. So this is a system of more something like 5,000 atoms calculation. And this is a zoom of this system nearby the region occupied by this small molecule here, which is supposed to inhibit the function of the enzyme. So this is a system that has been measured by experimentalists and then refined by people that work in biological, in structural biology. Then we use the atom position of the system. We give that to BigDFT. BigDFT calculates the electronic structure. It extracts the fragment and it extracts the interaction between the fragment. What are these fragments? These fragments are highlighted here with these colors. And these are not designed before. They are actually identified a posteriori out of the BigDFT calculations. And they actually resembles a lot the chemical groups of these small molecule. And not more than that, those chemical groups can be shown to interact with the amino acid of the enzyme that are also other fragments that could be identified a posteriori. So it's interesting to see that by applying our recipe, we can actually see that a protein is decomposed by amino acids. So we retrieve the biological intuition from a protein calculation made with this approach. So this is very reassuring because it's somehow telling us that we are dealing with reasonable quantities, and those reasonable quantities can also be applied on the molecules that are not in principle made of amino acids. So it's interesting because we have a comparison of fragments on equal footing, and we can draw interaction maps by using such kind of graphs. So you could see that with this graph, you decompose the small molecule fragments, and you see how strong are the chemical bonding between each fragment and the neighboring one. And we can even represent the interaction strength. So in a kind of tight binding like model that's come from other fields of computational physics, we may represent how stabilizing is the interaction between the various fragments. So this is giving us information on how important a particular fragment is in the binding between the protein and the small molecule or the drug, we could say. So this is a first example that shows that we started from material science and applied mathematics, and now we are dealing with quantities that are related to biology or somehow drug design. So we eventually can create fragment libraries of various molecules in the same spirit. This is an example that enables you to use BigDFT to see how you would decompose the system into various sub-regions and so on. So, of course, there has been a number of papers we have been doing with these kind of concepts, and those concepts are all based on the manipulation of BigDFT quantities originated from BigDFT, but they range in a community that is completely different from density functional theory calculations. So essentially, here you could see how these fragments are important in the various enzymatic pockets of the system. So if some of you are familiar with such kind of keywords, it could be interesting to see that indeed the density functional theory is now able to provide other characterization methods in these fields. So the main message is now that with BigDFT, we can characterize interactions between protein and proteins or other small molecules in a non-arbitrary way, totally unbiased, thanks to the high precision and high flexible framework that is provided by Dobeshi's wavelets. So in the interest of time, I think I will conclude my presentation by saying that we have been applying these on SARS-CoV-2 main quantities. We have been able to play with considerations around original wild type SARS-CoV-2 virus connected to the human or to the bat receptor. Then we have been able to play with the variants and find the new putative variants of Omicron that have been also found 2 years after our prediction. So this is an approach that somehow enables to identify biological insights. So we have been proving that this is possible, not only in drug design, but also in detoxification or other communities where a structural representation of the protein ligand system is available. So essentially, the idea is that in the case when one wants to use density functional theory for large systems by using large supercomputers, the idea is not only having high precise and high accurate data, but is also having insights on those systems. we have this framework we have been calling complexity reduction that comes directly out of the Dobeshi's wavelet property that we are using to measure interaction between building blocks of system. And we hope to create with this kind of framework new interdisciplinary collaborations which can range from applied mathematics to computational physics, passing through biology, but without forgetting the high performance computing aspect that is fundamental to treat such kind of calculations. So everything is somehow made possible by the usage of modern supercomputers and new architectures. That is one of the main activities of the BigDFT developers consortium. So this concludes my presentation, and I hope that the messages were clear enough. Also, the audio was clear enough for you. And I
Yeah,
really
thank you
look
so
forward.
much, Luigi. Luigi, it was perfectly clear. We can really see the passion and how this subject is important through your eyes. So it's really interesting to have such speaker to share,
Thanks.
I mean, all their knowledge. So thank you so much again. And please in the chat, if you have any question, raise your hand, and I think Luigi will be really happy to answer you.
Absolutely.
Mm. Don't be shy. It's your opportunity to talk with our expert. It could be a really interesting start for a discussion. Oh, we have a question.
Yes. Uh, can BigDFT locate metastable configurations on reaction pathways? Yes, absolutely. This is one of the main topic of attentions we have been working on in the first part of a BigDFT project. And of course, this is still possible nowadays. So we have connected the BigDFT to various potential energy surface methods. Initially, we used nudged elastic band, so we have a NEB engine that uses BigDFT to evaluate the uh, synthesis or somehow the reaction coordinates of a system for which we have a double-ended approach. If we don't have the double end, we could also have been using the open-ended method. One example was the activation relaxation techniques. And essentially, this is another way of connecting BigDFT results to reaction pathways. We also have the splined saddle method for finding reaction pathways. So the point there is that any kind of external method that employs force field-like quantities, energy and forces, can be linked with BigDFT. The advantage here is that as we can increase the precision of the calculation, we can find the transition state for a given set of approximation with a high level of accuracy and a high level of quality because we can reduce the noise on the computational forces. So yes, definitely. I hope this answers the question. Of course, when it goes to very large system, you need to keep into account the cost for doing those calculations. But it's totally possible to imagine a workflow where one first perform an initial optimization with, say, force field of a very large system, and then constrain all the part of the atoms except the main active region, and then uses the same approaches for those part. Yes, so that's the point. There is another question about what do you expect from a exascale of Alix Recoq in 2026? Which breakthroughs are foreseeable using BAT analysis? Absolutely, this is an important opportunity. I have been briefly discussing about the various sub-libraries of BigDFT and the way in which BigDFT is conceived, but I didn't discuss on purpose today on the technical points which are leveraging the usage of BigDFT on supercomputers. So one of the technical points is the GPU acceleration. So BigDFT has been using a GPU since the early days of GPU. We are using graphic cards for accelerating the calculations since 2010. The point is that this enabled us to use a software development approach that is always based on heterogeneity on the architecture. So there is this Poisson solver part of BigDFT, which is now being ported on every possible modern architectures. So we are actually finalizing a manuscript that showcase the fact that we have a selector that enables to use the Poisson solver on any kind of modern platform that is available nowadays, from ARM GPU to NVIDIA GPU or PVC or AMD GPU to ARM CPU. Every architecture, including traditional CPU, of course, can be used with this Poisson solver. Now, the Poisson solver as BigDFT is at the base of very highly accurate density functionality theory treatment. So the Poisson solver can be used heavily when it comes to use hybrid functionals. This is the main message in the main keyword in our community that would enable calculations of very challenging systems. We have been showing in the past that thanks to GPU acceleration, those hybrid functional can be executed with the same level of wall time, with the same computational wall time of a normal traditional functional. So I'm really expecting the fact that thanks to new GPUs and new architectures, we could make approaches that were very difficult 10 or 20 years ago. 20 years ago, they were totally impossible. Nowadays, accessible to the community. So we couldn't not anymore, not only go large in terms of larger system, but also much more accurate. Another approach is the high throughput part. You see that in this protein calculation, you need to investigate many snapshots of the system, modify fragments, change the structure, and so on. Supercomputers like exascale treatment enables you a high throughput approach of large scale quantum mechanical calculation with very highly accurate functions. So this unlocks new opportunity in a way that is definitely very, very stimulating for our community. Another question is, will BigDFT code development compete for one of the lighthouses in the future COE calls? Yeah, I think I should mention that at present, BigDFT is one of the lighthouse code of the Max COE consortium, and it has been so also in the previous call. So the Max 2 consortium. Of course, the consortium is among it includes also other codes like Quantum Espresso or Siesta or Fleur or Yambo code that are based on different formalisms. So I think that the different formalisms that are included in the Max COE consortium represent a very nice opportunity because they can tackle systems that are different with each other, that can reach different communities, so they would have a potentially very large impact. We are discussing with the rest of the consortium about the more suitable strategy for the next COE call, taking into account the requirements that the next COE call is putting on the various consortia. But yes, we are. The discussions are presently ongoing, and of course, all options are on the table at present. I am really excited on the point of seeing where these new formalisms that it's now used since a while can bring the let's say impact of DFT in all the communities that somehow can be connected to that. So yes,
Okay.
this is.
I think we don't have any more question. Thank you so much, Luigi.
It's a pleasure.
And yeah, thank you also to all the attendees. Um, and if you are interested, our next event within EUPEX is this workshop at High Peak. So please feel free to join. It will be also yes, I'm seeing the clap in the chat. It's funny. Okay. So yeah, it will be also really interesting. We will talk about energy topic. We'll also showcase other application and some tools. And we'll talk about ARM-based architecture and also a bit about sovereignty. So yes, if you are interested, please, yeah, join us in High Peak. And thank you so much. Have a nice lunch. It's time to eat. And bye.
Thank you. Bye. Thank you very much. Ciao.